Hi, welcome to lecture on 4.4 on the product of transforms. So today we're going to be looking at how you can take advantage of, or how to compute the inverse Laplace transform of a product of transforms. So sometimes we'll be able to recognize this thing that we're trying to find the inverse Laplace transform as some Laplace transform that we recognize times another Laplace transform that we recognize. And this theorem tells us that in order to compute this inverse Laplace transform, we just take the function f of t, which comes from this Laplace transform, and we multiply it with a special type of multiplication times the function g of t, which comes from this guy here. And what is this special type of multiplication? It's called a convolution of f of t and g of t. And it's written in this way. So this is a special type of way to multiply two functions. And how do you multiply these two functions in this way? So the convolution of f and g is equal to this following integral. So we're integrating with respect to tau, so d tau. We're going to integrate f of tau from 0 to t. So we're going to go from f of 0 to f of t. And then we're going to multiply that by g of t minus tau. Now this is going to go from when tau is 0, this will be t. And when tau is equal to t, then this thing will be equal to 0. So this term is going from 0 to t, this guy, and this guy is going from t to 0. So they're kind of going in opposite directions, and we're multiplying them together and integrating them. So this is called the convolution of f and g. And it shows up in a number of different places with respect to other transforms, like the Fourier transform as well. So there's a version of this theorem for the Fourier transform. But this is the idea. So when we go from the Laplace space, when we're multiplying in the Laplace domain, that corresponds to multiplying in the time domain, but we multiply using the convolution. Now, another way that's often, we often write this convolution is as the following, right? To sort of emphasize that it's a single function, which we refer to as f star g, right? So it's a single function of t. So that's the way you can think of what happens when you convolve these two functions together, you get a new function. Okay, very similar to like when you multiply two functions together, you get another function. So no surprise there. So some other properties of convolution. So one is that it doesn't matter what order you do it. So f convolve g equals g convolve f. So the order doesn't matter, and it's pretty easy to see that. Also, if you multiply the convolution by a scalar a, then you can just multiply the function f by a and then convolve it with g. So, so that works that way. And in particular, if a is 0, then we get 0 convolve g is equal to 0 times this. So that means whenever you convolve 0 with a function, you get 0. So that's also kind of like what you would expect with multiplication. 0 times anything is 0. And then it also has this property as well that we're familiar with multiplication. So when you convolve f with a sum of functions, that's the same as doing f convolve g plus f convolve h. Now, what about, what times g is equal to g? So normally you would think it's just 1 times something is equal to this. But for the convolution, it's not 1. So 1 is not going to work here. So instead, what we need is a special function called the Dirac delta function, which we won't go into too much detail right now, but it's a function that is used a lot in physics and engineering. And in some respects, it's not actually a function, it's more of an operator that gets used inside of an integral. So it's not technically a function, but I guess we can say some things about this. It's a very kind of interesting thing that it's 0 everywhere except, so when t is not equal to 0, then this thing is 0. And when and when you integrate this over all t, then you get 1. So it's basically 0 everywhere, but when you integrate it, it equals 1. So that is what the Dirac delta function is. Okay, so we're not actually going to use that today. We're just going to be looking at some examples where we find the inverse Laplace transform using this convolution theorem. Okay, so let's get started with that. So let's see. We want to compute this inverse Laplace transform. And we notice that this is like 1 over s times 1 over s minus 3. And we know what the inverse Laplace transforms of those two functions are. The first one is what? So the inverse Laplace transform of 1 over s, that is 1. And the inverse Laplace transform of 1 over s minus 3 is e to the 3t. Okay, so just keep that in mind over there. Put that in a box. So that means that if we want to compute this inverse Laplace transform, we can use convolution. So it's going to be 1 convolution with e to the 3t. And how do we compute that? That's going to be the integral from 0 to t. And then this will be just 1. So it's going to be f of tau, but that's just 1. And then we have, I wonder if we should maybe do it in the other order. That might be a bit easier. Because then, I mean, either way, it doesn't matter. But we'll write it in both ways, and then we can kind of decide which way is easier to do. So we can do it like this, or if you want, because it doesn't matter the order that we do it in, we could also do it like this. And I just feel like that second thing is just kind of easier. I would say it's a little bit easier. It looks simpler. So let's do the second one. So you can think of this as e to the 3t convolve with 1, right? So we know those two things are equal. So let's go ahead and so I'll just put that in parentheses there, just to remind us what we're doing. Okay, so this is a pretty simple integral. So it's going to be 1 over 3 e to the 3 tau. That's the antiderivative. And we're going to evaluate that between 0 and t. So we'll get 1 over 3 e to the 3t, and then minus 1 over 3 e to the 0, which is 1. And so there's our answer. Okay, and why don't we just factor out the 1/3? Okay, put that in a box. Okay, so now let's check. Let's just check this because we can compute the Laplace transform of that pretty easily. So what is the Laplace transform of 1/3 e to the 3t minus 1? This is equal to 1/3 times the Laplace transform of e to the 3t, which is 1 over s minus 3, and then minus 1, which is 1 over s. So let's put those together. So we get s minus s minus 3 over s times s minus 3. So just combining those fractions. And it's pretty easy to see that this s cancels that s. We're left with plus 3. And then dividing by 3 gives us 1 over s times s minus 3. So just to check it off, that is what we started with. So good thing to easily check. Okay, so of course, we could have done this with partial fractions as well. So that would have been another way to do it. And if we did partial fractions, then we would have had like, just sort of quickly write this over here, a over s plus b over s minus 3. And we would have found that a is negative 1/3 and b is positive 1/3. So that's another way to do it. But here we did it with convolutions. Okay, so let's do another one. Now this one is where this convolution theorem really pays off, because this is a type of convolution that we were not able to do with partial fractions. So we really do need this convolution theorem to do this. Okay, and if, for example, if you look at the table of Laplace transforms, this guy does appear on the table of Laplace transforms, and it's a very complicated thing. So in fact, that's what we're expecting to get. So we'll see that on the table of Laplace transforms, the Laplace transform, or the inverse Laplace transform of 1 over s squared plus k squared squared is equal to 1 over 2k cubed times sine kt minus kt cosine kt. Okay, so it's I'm going to erase that for now. Maybe we'll use that in the future, but let's erase that. So you can see it's quite complicated, but this is what we're expecting to get. Okay. And in particular, what's interesting is that you'll notice in the inverse Laplace transform, we're getting this like cosine, t times cosine kt. And this is an indication, if you're doing mechanical vibrations, that you have a resonance occurring, right? So you have the amplitude of this vertical, or of this mechanical vibration is getting larger and larger as time is increasing. So that's why these types of Laplace transforms are important. So if you do end up seeing something like this in your the solution of a differential equation for mechanical vibrations, that's an indication that you have some resonance occurring. Okay, so let's use the theorem to do this. So of course, the inverse Laplace transform of 1 over s squared plus 9, we know what that is. That is sine 3t. So we know that one. So let's use that. So we have 1 over s squared plus 9 times 1 over s squared plus 9. So this is going to be sine 3t convolve with sine 3t. Okay, so in this case, it doesn't matter what order we do it in. It's the same thing either way. So it's going to be sine 3 tau times sine of 3 t minus tau, and then d tau. Okay. So maybe I should put parentheses around this to be clear what's going on. I'll put a dot there to indicate multiplication. Well, we don't need the dot. Okay, so this is the integral we wanted to use. Now, this type of integral requires us to use a certain trig identity in order to do it. So there's these special trig identities called product to sum trig identities. So we have a product of trig functions here, and we want to write down a sum of trig functions and then integrate that. Okay, so what is these trig identities that we need? So I think I've got it here. Yeah, here they are. So let's bring these up here. Okay, so which one is the one that we would like to use? So we have a product of sine functions. So that means that we're interested in using this one right here. Okay, so there's the product to sum trig identity that we would like to use. So so of course you can definitely like just look this up if you need it. These are things that may be kind of hard to remember, but if you're interested in kind of a quick way to figure out these product to sum trig identities, I thought I'd show you a little trick that uses linear algebra to do it. So the idea is that you start with, let me see, I'll just put it right here. Okay, so here's our unit circle. Let's see, I think I can do a circle and then put it right there. Okay, good. Let's see, just clean that up a little bit. Okay, that works. That's perfect. Okay, so what is the idea? So if we want to rotate by an angle alpha, say this is alpha and then this is beta. So how can we go from this alpha angle to this beta? So first of all, we know that this point here is going to be cosine alpha sine alpha. And we also know that you can rotate by an angle of beta as follows. So if you want to rotate maybe a vector, so rotate maybe like xy points. So how do you rotate xy points? So you multiply by this rotation matrix. So cos beta, sine beta, minus sine beta, and cosine beta. So if you want to rotate the an xy point by an angle of beta, then you can do this. And how do you multiply these together? So it'll be x times cosine beta minus y times sine beta. So if you're familiar with matrix vector multiplication, this is the idea. So then x times sine beta plus y times cosine beta. Okay, so what does this mean? So that means that say I'm going to use this as my xy. So that tells us that if we want to get cosine alpha plus beta sine alpha plus beta, which is this point up here, right here. So that's this point here, cosine alpha plus beta sine alpha plus beta, that's that point. So to go from here to here and rotate along an angle of beta, we just multiply by this matrix here, this rotation matrix. So this is going to be equal to this rotation matrix times the point that we're starting with. So the cosine alpha sine alpha. And when we multiply this out, what do we get? We get cosine alpha cosine beta minus sine alpha sine beta. So that's the first entry. And then the second entry will be cosine alpha sine beta plus cosine beta sine alpha. So that's it. So we just combined a couple of ideas together. So that the two ideas that, well, really one idea, which is if you want to rotate a vector xy by an angle of beta, then you just multiply by this rotation matrix. So that's really the only idea that we needed. And now we're getting a couple of useful trig identities. We're getting that cosine alpha plus beta is equal to this, and sine alpha plus beta is equal to this. And these are the identities that we need in order to get these product to sum identities. Okay, so how does this work? So we have, we have this is equal to this, right? And if I also plug in minus beta, well, what is cosine of minus beta? Cosine is an even function, so when you put a minus beta in there, it doesn't change anything. So we just get cosine beta again. However, sine is an odd function, so when you do sine of minus beta, you end up getting minus sine of beta. So we end up having this now. And now we're almost done. We just add these together. And you notice when we add these together, this term and this term are going to cancel. And so we're going to be left with cosine alpha plus beta plus cosine alpha minus beta is equal to 2 cosine alpha cosine beta. And that's that first trig identity right there. So there we got our first trig identity. Now what about the second one? So I guess we already see what we should do. We take this one, and we take, the first one, and instead of adding them together, we're going to subtract. And now these two terms are going to cancel. So we're left with cosine alpha minus beta minus cosine alpha plus beta is equal to 2 sine alpha sine beta. And there's our second trig identity that in fact, that's the one we're going to be using. And then there's one more trig identity that we can get from this. So we'll take this, and that is equal to this guy. And we'll do the same trick that we did before. So we'll replace the beta with a minus beta. So we make this a minus. Then the sign of beta is going to change sign. So we'll end up getting a negative here. I just need to make a little bit more room for this. Maybe I'll just move this over a little bit. So I get a minus there, but then the other one I don't get a minus, right? Because cosine is even. So cosine minus beta is just cosine beta. But because here's the sine beta, I get a minus sign. And now we just add those together. And we get 2 cosine beta sine alpha. Okay. All right, so that's our a quick sort of summary of this product to sum trig identities. So we'll be using the this third one here. Sine alpha cosine beta. Yeah, that's what I had. Sine alpha cosine beta. Okay, so I wrote it in a different way, but that's fine. Okay, so let's go back now to our problem. So what is this function that we're looking at? So we want to compute this. So we have this product of functions, and we want to use the that trig identity in order to compute it from to change it from a product of functions of trig functions to a sum of trig functions. So it's going to be this one here. So we're going to have, so we'll divide by 2, right? So this 2 will be over here. So we're going to have cosine of the difference minus cosine of the sum. Okay, so 1/2 cosine of the difference. So now I'm going to take this minus this, and that will give me 6 tau minus 3t, and then minus cosine of the sum. So now when we add these together, 3 tau plus this, so the taus will cancel, and we're just left with 3t. And that will be especially nice to integrate because we're integrating with respect to tau. So that's just a constant. So that's why it's so nice to integrate that. Okay, so this first term, so let me just take the 1/2 out. So the first term, what is the antiderivative of that? So it'll be a sine of 6 tau minus 3t, and then we need a 1/6 in order to take care of that. So then if we take the derivative of that, we get the right thing. So remember, we're doing the antiderivative with respect to tau. So t is just a constant here. It's easy to forget that. And then this is just tau times cosine 3t. And then we'll evaluate that from 0 to t, integrating from 0 to t. Okay, so let's see what we get here. So when we plug t in, we get 1 over 6 sine of 6t minus 3t. So I'll just write that out. And then minus t times cosine 3t. There's that resonance term appearing. That's the one we were talking about before that indicates resonance. And then we have minus 1 over 6 sine of 0 minus 3t. So I'll just write minus 3t there. Oh, I'll write 0 minus 3t because we need to simplify this anyway. And then this will be plus 0. When we plug in 0 into tau, we get 0 times cosine 3t, so that's 0. Okay, let's simplify this. So here we have sine 3t, and here we have sine negative 3t. So this negative sign, because sine is an odd function, this negative sign pops out, and it will make this minus here a plus. So we're going to have sine 3t plus sine 3t. So this will give us 2 of those. So we'll get 2 over 6 sine 3t. And then here we have minus t cosine 3t. Okay. So this is 1/3. Oh, let's see, wait. Oh yeah, I did make a mistake. I remember. I did make a mistake. So this is actually, okay, I'm sorry I made a mistake here. I told myself not to make this mistake, but I did. Okay, so this is actually going to be 1 over 9 times, and then these have to be 3 up here. Yeah, that was my mistake. I even made it here. Quite silly. Yeah, so that's supposed to be 3 in the numerator there. So to get those 3's up there, we have to divide by 9. So that means this is 1 over 9, 1 over 9, and all the way down, we need to plug in this 1 over 9 here. So then this becomes 1 over 18, 1 over 18, and 1 over 18. Okay. All right. I made that mistake twice. I made it before, and then I made it again as I'm recording. All right. So this is 1/3. So when I take the 1/3 out, I get 1 over, that'll be 54. Yeah. 3 times 18, that's 9 times 6, 54. Okay. So 54, and then this will be sine 3t. And then this will be, so when I take the 1/3 out, I need a 3 there. So that'd be 3 times 1/3. So take the 1/3 out, yeah. So I get this. Okay, and now just to compare, so the general formula of the inverse Laplace transform of 1 over s squared plus k squared squared is equal to 1 over 2k cubed times sine kt minus kt cosine kt. All right, and so this matches. So we get, so in this case, k is 3. So we would get 2 times 27, which is 54, and then everything else matches. So we got 3, 3, 3 matches. Okay. So that's how we compute the inverse Laplace transform of something like this. We use that convolution theorem. And so we just have to do this integral that requires us to use the product to sum trig identity. And other than that, it's pretty straightforward. Okay, so this is just to note sort of the general formula that we have. Let me put this in a nice box. So there we go. So that's the formula from the table of Laplace transforms. All right. Okay, here's another one. So, this is going to involve that same thing. So I have to remember not to make that mistake that we made before. So of course, we see that f of t is equal to a product of transforms. It's going to be 1 over s squared, and the inverse Laplace transform of 1 over s squared is t, and then we also have the inverse Laplace transform of, and don't forget this, k over s squared plus k squared, and that is going to be sine kt. Okay, so let's not forget that. So, so this will be 1 over k times 1 over s squared times k over s squared plus k squared. Okay. All right, now by the convolution theorem, this is going to be 1 over k times t convolve with sine kt. Okay. And I'm just trying to decide which order I want to do that in. Maybe I'll flip it around and I'll do sine kt convolve with, let's put it in parentheses, convolve with t. Okay. So let's do it in that order. So we get 1 over k, integral from 0 to t, and then we'll have sine k tau, and then that will be times t minus tau, d tau. Yeah. So there's our f of tau, and this is our g of t minus tau. So we plug t minus tau into this function, so it becomes just t minus tau. Okay, so now this will split up into 2 different integrals. So we'll have a t times this, and that'll be an easy integral to do. And then the other one will be a tau times this, and for that we need to use integration by parts. So let's write this one out first. So we have t sine k tau d tau minus integral from 0 to t of tau sine k tau d tau. I guess the other way would have been equally nice to do. So whichever way you want, but it's nice to just have sine k tau there. Okay. So let's do this first integral. This will be quite straightforward to do. So this is going to be, let's see, maybe I'll put parentheses here. And then I'll use brackets here. Okay, so let's do this integral. So t is just a constant here. This will be a cosine k tau, but then we're going to need what? Let's see, just move. Oh, it's not responding. 1 second. Okay, my pen battery died, or my Apple Pencil. The battery died in it. Okay, that's why I wasn't responding. Okay, so where were we up to? Right, so this, let's see, we need here. So this will be, yeah, let's just delete that. So we're going to get minus t over k, and then cosine k tau, evaluated from 0 to t. Okay, so let's just check. So if we take the derivative of this, then it'll become negative sine kt times k. So that'll cancel those, and we'll end up with this. Okay, perfect. So there's the integral there. And then we have this other integral, which maybe we'll just leave it like this for now, and then we'll do the integration by parts after we've simplified this first term. So this first term is going to become negative t over k cosine k t minus, which becomes a plus, t over k times cosine 0, which is 1. So that's what we get for this first term. Okay. And then minus this. All right. Not happy with that tau there. A little bit better, not perfect. Okay, so that's what we have there. Let's just make a little bit more room here. So add a page. Okay, so I guess let me just take care of this thing separately, and then we'll plug it back in. So let's sort of focus just on this integral here, so I don't have to keep writing all that stuff. So because we're going to do integration by parts, d tau. So integration by parts, I'm going to want to take the derivative of this. So first thing, I need to integrate this term. So it'll be tau, and then the integral of that will be cosine k tau, and then as we just saw, we need a minus 1 over k. That will be the integral of that. Okay, so then that will be evaluated between 0 and t, and we have minus, and this is where integration by parts is quite nice, because we take the derivative of that tau, and that is just 1, and then we have this integral over here. So maybe I'll just write this as negative 1 over k cosine k tau d tau. Okay. All right. Maybe I'll just copy this. Copy. So, okay, on the next page, so let's continue this calculation. So the first term is going to become minus t over k cosine kt minus, and that will be a plus. Oh no, that'll just be 0, right? Because I put 0 into tau, so I just get 0 there. Okay, so let's write that in. So I get 0. All right. And now minus, let me get rid of that 0 because I need more room here. All right, so let's integrate this. So this will become sine k tau, and I need to divide by k. So I'll get minus 1 over k squared from 0 to t. Okay, let's just pause and make sure. If I take the derivative of this, then what do I get? So derivative, it will be cosine times cosine k tau times k. So that'll make this minus 1 over k, which is what we have. Okay, that's perfect. Okay, so then let's put this together. So we have minus t over k cosine kt minus 1 over k squared sine k t. And when I put 0 in there, sine of 0 is 0. So I just get that. So in the end, let me put this term in the front because it'll be minus minus, which is plus. So that'll be 1 over k squared sine kt minus t over k cosine kt. Okay. Okay, great. That's what we needed. So let's just draw a little line here. So therefore, f of t is what? So here it is right here. So this is f of t. That, and then this this integral here, this is equal to this term right there. So I'll just plug that in. So that'll become minus 1 over k squared sine kt plus t over k cosine kt. Okay, what can we simplify here? Okay. This and this cancel, which makes me almost think if I did it in the other order, maybe it would be easier. Then I wouldn't have this stuff appearing. But anyway, so this stuff cancels, and we're just left with this and this. And why don't we let's see, pull out a 1 over k squared. So we'll get 1 over k cubed, and then this will be k times t minus sine k t. Okay. All right, and let's see, what did we start with? So it was this one. So 1 over s squared times s squared plus k squared. All right, so let's summarize. So therefore, the inverse Laplace transform of 1 over s squared times s squared plus k squared is equal to 1 over k cubed times k t minus sine k t. And actually, this we can check. So why don't we check to make sure that we did the right thing? Because it's very easy to take the Laplace transform of this function on the right. So let's check. The Laplace transform of 1 over k cubed times k t minus sine k t. Let's just move this here. Need more room. So this will be equal to 1 over k cubed times the Laplace transform of k times t, which is k over t s squared, and then minus k over s squared plus k squared. And we get 1 over k cubed times, well, let's take one of those k, let's take that 1k out, so we'll get 1 over k squared. So then it will be 1 over s squared minus 1 over s squared plus k squared. So that's s squared plus k squared minus s squared over s squared plus k squared. And it looks like everything's working out perfectly. So that cancels that, and then we're left with this, that cancels that, and so we get 1 over s squared times s squared plus k squared. Okay, so it works out. So we get that, and that checks out. Okay, so of course, another way that we could have done this with partial fractions, so this one we could do with partial fractions because we would have 1 over s squared plus k squared, and we can write that out as a over s plus b over s squared plus cs plus d over s squared plus k squared. So we could have done it this way as well. And what would we have had if we had done this? So this a would have been 0, then the b would have been 1 over k squared, and the c would have been 0, and the d would be minus 1 over k squared. So that's what would have happened. And that probably would have been a lot easier, I would think. So I think with doing it with partial fractions would have been a lot easier. So let's just write that down. So we would get a equals 0, b is 1 over k squared, c is 0, and d is minus 1 over k squared. Okay, so I won't go through the details of that, but that's what would have happened if we did this partial fractions. And I'm thinking that would have been a lot easier than what we did, which was, let's just review. So we were using this convolution to do this. So we did the convolution, and that meant we had to compute this integral. That integral required us to use partial integration by parts. And then when we combined it all together, we got this. So that was kind of a lot of work, and probably doing it with partial fractions would have been a lot easier, I think. Okay, so let's see. I think this is the last one, so one more. Yeah, this is the last one we want to do. So let's do one more of these. So again, this one we could do with partial fractions, or we could do it with convolution. So either way would work. So so let's do it with convolution. So we can see that this is a product of 1 over s minus 3. So the inverse Laplace transform of 1 over s minus 3 is e to the 3t, and the inverse Laplace transform of s over s squared plus 1 is equal to cosine t. Okay. So let's use convolution to do this, the convolution theorem. So the convolution theorem says that the inverse Laplace transform of 1 over s minus 3 times s over s squared plus 1, this is going to be equal to e to the 3t convolve with cosine t. Okay, I think I want to put cosine first. So cosine tau times e to the 3t minus tau. Okay, so this is one of these problems where we need to do integration by parts twice. So the first time we do integration by parts, this cosine will become a sine because we're going to take the derivative of it. And then the second time we do it, the sine will become a cosine again. So we're going to get a sine and then a cosine, and then we will take that cosine term that we get down here, and we will move it back up here, and we'll solve. So that's the idea. Okay, so let's do that. So integration by parts, I'm going to first need to integrate this. So integrating this is going to be what? So integrating with respect to tau. So that will be e to the 3t minus tau. And then what do I need to multiply by? So if I take the derivative of this, I will get this times minus 3. So I need to divide by minus 3. So negative 1 over 3. Okay, so that's what we'll get there. And then this will be evaluated between 0 and t. And we'll do minus integral from 0 to t. Oh, you know what? I should just do this whole thing without those limits. That'll be a lot easier. So let's do the following. I'm just going to just separate this out. We'll figure out what this antiderivative is first, just on its own. What is the antiderivative of this? could almost factor out that e to the 3t. Yeah, let's do that. Let's factor that out. So the e to the 3t can be factored out to the front. So we're going to be left with negative 3 tau here. So this is the integral that we're really after, and that will simplify things a lot. Yeah, let's do that. Save some space here, so that collapses. Maybe I can make this all fit. So yeah, let's do this. So this will be negative 1/3 cosine tau e to the negative 3 tau minus, let's get rid of that stuff. So it'll be that minus integral of, now I take the derivative and I get 1/3 sine tau e to the negative 3 tau d tau. Okay, good. All right. That looks really good. Okay, so now, I might need a little bit more space here. So let's put this over here. So we have minus 1/3 cosine tau e to the negative 3 tau minus, now we do another round of integration by parts. So we'll get minus 1/3, and now we're going to do another integration by parts here on this sine tau e to the negative 3 tau. Okay, so like before, we put minus 1/3 sine tau e to the negative 3 tau, and then minus, yeah, I need more room. Need more room here. Minus integral negative 1/3. Take the derivative, which is cosine tau e to the negative 3 tau d tau. Yikes. Okay, let's move that over a little bit more. Okay, all right, there it is. Great. So now we can simplify this. Minus 1/3 cosine tau plus 1/9 sine tau, and that's multiplied by e to the negative 3 tau. Okay. Then we have to be careful with the sign here. So we have plus 1/3 multiplied by minus 1/3. That'll be a minus 1/9 integral of cosine tau e to the negative 3 tau d tau. Okay, and this is what I promised would happen. So we have this guy here is equal to this one right here. So we did integration by parts twice, and we ended up getting the same thing back again. Now what we do is we take this term here, and we're going to move it over there. So we'll get a 1. Yeah, so let's just write it out. So therefore, 1 plus 1/9 times this integral is equal to this. That's not going to fit. Let's make it smaller. There. Okay. So what is this over here? We have 10 over 9. And then that's equal to this stuff again. Now it fits. Okay. And then finally, we multiply both sides by 9 over 10. Multiply by 9 over 10. Okay, let's see. I'm going to bring that 9 inside. So I'm going to leave the 1 over 10 outside, bring the 9 in. I get minus 3 cosine tau plus sine tau e to the negative 3 tau. Okay, great. That's what we needed. All right, now back to this integral that we want to compute. So let's copy that. So remember that f of t is equal to this. And that in turn is equal to, if I factor out the e to the 3t, factor that out, it's equal to that. Maybe I could have written that up here. Okay. All right. So that's what we wanted. And maybe I'll just highlight this as well. Okay. All right. So that's the idea. So we have this, and now we know what that integral is equal to, and it is equal to or the antiderivative of this is equal to 1 over 10 negative 3 cosine tau plus sine tau e to the negative 3 tau, and then evaluate from 0 to t. Okay. What do we get? Okay, so replace the taus with t, and then minus 1 over 10 minus 3 times 1 plus 0 e to the 0, which is 1. So times 1. Oops. Okay. So therefore we get what? Let's see. So that whole thing on the right is just going to be plus 3 over 10. So let's factor out the 1 over 10. And then actually we can bring the e to the 3t inside. So we get negative 3 cosine t plus sine t plus 3 e to the 3t. Let me just double check this. So this guy here cancels that one. This 1 over 10 comes out here. So we're left with this. And then this is 3. And that times that is this. Okay, I think that's it. Okay, so what does that mean? So therefore, the inverse Laplace transform of s over s minus 3 s squared plus 1 is equal to this. Okay, and let's check that, because I think we know the Laplace transform of everything in here. That, and that, yeah, we can do this. So the Laplace transform, oops, so we'll check. The Laplace transform of this is equal to 1 over 10 times minus 3 s over s squared plus 1 plus 1 over s squared plus 1 plus 3 times 1 over s minus 3. Minus 3 s plus 1 plus 3 over s minus 3. Okay, so combine those fractions together, we get this. Let's see, FOIL this out. Let me just change the order of the denominator. So it's in the same order as what we started with. Okay, so that cancels that. That cancels that. And we're left with 9s plus s, which is 10. Well, why don't I just, now I know I get 10s, so that 10 will cancel with the 10 on the outside. So I'm left with s over s minus 3 times s squared plus 1. Okay, so exactly what we started out with. Perfect. Okay, so we know that we did everything correctly. And as I mentioned at the beginning, did I actually write out the partial fraction approach here? No. So if you wanted to do with partial fractions, then you would have done the following: s over s minus 3 times s squared plus 1. You would have written that out as a over s minus 3 plus bs plus c over s squared plus 1. And what would have happened? It looks like, so here it is right here. So this is the one that we're interested in. So it looks like the a would have been 3 over 10. So let's write that down. So a would have been 3 over 10. What would the b have been? Chana, just wait. I'm in the middle of a lecture here. So the b would have been minus 3 over 10. And the c would have been 1 over 10. Yeah, 1 over 10. Okay. So that probably would have been a lot easier than what we did, right? So using, again, in this case, using partial fractions would have been the way to go. I think in order to do this inverse Laplace transform, would have been a lot easier to use partial fractions. Okay, so so that's it for that example. But all of these Laplace, all these questions, we're supposed to do it using the convolution theorem. So that's what we did. So here we use convolution to do this one. It required us to do this integration by parts twice, which was not a lot of fun, unless you like doing integration by parts. But who likes doing integration by parts? Not a lot of people. This one, also we could have done using partial fractions. However, this one here, the one that involved some resonance, this one, we definitely needed to use this theorem, convolution theorem, to do that. And this one here, of course, we could have done this without the convolution theorem, but we should start somewhere easy initially. So that's it. That's the convolution theorem here. So using this and this is a way to do some of these inverse convolutions or inverse Laplace transforms. All right, well, thanks so much for watching. I need to let my dog out of the room, so I will see you in the next lecture. Thanks for watching.